Regarding the installation of capacitor banks, let's address several key considerations. First, the approach of using an enclosure with a splice to feed each capacitor unit may not be the most efficient. A more streamlined approach involves running parallel 400 cm conductors directly from the disconnect to each capacitor bank unit. This eliminates the need for a splice enclosure, which can add unnecessary cost and complexity to the installation. The location of the disconnect is another important aspect. It does not necessarily need to be immediately adjacent to the capacitor banks. The primary requirement is that it be within sight of the equipment. The scenario where the disconnect is located about 15 feet away from the capacitor banks on the same side of the gear should generally be acceptable, provided it meets local codes and regulations. Let's discuss current calculations and protection. Based on calculations, the maximum current that the capacitor banks will draw at 600 volts is approximately 583 amps. The long-time pickup setting of 560 amps on the DS206E breaker in the main switchgear should offer adequate protection for the capacitor banks. It is crucial to verify these settings with the manufacturer's specifications and local electrical codes to ensure proper coordination and protection. Conduit selection is also a significant decision. The consultant's specification of rigid steel conduit, or RSC, likely stems from its robustness and durability. RSC is generally more resistant to physical damage during installation and subsequent maintenance activities compared to electrical metallic tubing, or EMT. While EMT is a more cost-effective option, it is more susceptible to dents and other forms of damage. The ultimate decision regarding conduit type rests on a comprehensive assessment of the installation environment, potential hazards, and budgetary constraints. Now let's address the conductor sizing. The recommendation to use parallel 400 cm conductors for the capacitor bank installation is a reasonable one. These conductors should be sufficient to carry the required current, and they offer a cost advantage compared to larger conductors such as 500 cm. Here is a more detailed explanation of each of the aspects. Conductor sizing for capacitor banks involves several steps to ensure adequate ampacity for the application. The initial step is calculating the rated current of the capacitor bank using the kilovar rating and the system voltage. Use the formula amps equals kilovars times 1000 divided by the square root of 3 times the line-to-line voltage. This calculation provides the base current that the conductors must carry. The National Electrical Code, or NEC, requires that capacitor circuit conductors have an ampacity of not less than 135% of the rated current of the capacitor. This 135% factor accounts for potential harmonic currents and overloads that can occur in capacitor circuits. The formula for this is minimum conductor ampacity equals 1.35 times the capacitor rated current. The NEC provides ampacity tables such as Table 310.16 that list the allowable ampacities of various conductors based on their size, insulation type, and installation conditions such as ambient temperature and the number of conductors in a raceway. These tables are used to select the appropriate conductor size that meets or exceeds the calculated minimum ampacity. When conductors are installed in parallel, the ampacity of each conductor must be derated according to NEC Table 310.15. The derating factors depend on the number of conductors in the raceway or cable. Parallel conductors are often used to achieve the required ampacity when a single conductor would be too large or impractical. To determine the conductor size, divide the total required ampacity by the number of parallel conductors to find the ampacity required for each conductor. Then, use the ampacity tables to select a conductor size that meets or exceeds this value. For example, if the calculated minimum conductor ampacity is 650 amps and two parallel conductors are used, each conductor must have an ampacity of at least 325 amps. Review the manufacturer's specifications for the capacitor bank to identify any specific requirements or recommendations for conductor sizing and protection. Some manufacturers may recommend larger conductors or specific types of insulation to account for particular operating conditions. Here is an example to illustrate the conductor sizing process. Consider a 400 kV capacitor bank operating at 600 volts. Firstly, calculate the capacitor rated current using the formula amps equals kilovolts times 1000 divided by the square root of 3 times the line-to-line voltage. Amps equals 400 times 1000 divided by the square root of 3 times 600, which equals approximately 385 amps. Secondly, determine the minimum conductor ampacity using the 135% factor. Minimum conductor ampacity equals 1.35 times 385 amps, which equals approximately 520 amps. Thirdly, select the conductor size. If using parallel conductors, and 2 conductors are used per phase, the ampacity required for each conductor is 520 amps divided by 2, which equals 260 amps. From NEC Table 310.16, a 400 mcm copper conductor with a 75 degrees Celsius insulation rating typically has an ampacity of around 335 amps, which exceeds the required 260 amps. Therefore, using 2 400 mcm conductors per phase would be adequate. When installing capacitor banks, the disconnecting means must comply with NEC requirements to ensure safety during maintenance and emergencies. The NEC mandates that all ungrounded conductors of a capacitor bank must be simultaneously disconnected from the power source. This requirement is to prevent any residual voltage or current from remaining in the capacitor bank when it is de-energized, which could pose a shock hazard to personnel working on the equipment. A circuit breaker or a switch can serve as the disconnecting means provided it meets the NEC requirements for interrupting the fault current and is readily accessible. The disconnecting means must be capable of interrupting the maximum fault current available at the capacitor bank location. This is crucial to ensure that the disconnecting means can safely de-energize the capacitor bank under fault conditions without failing. Circuit breakers used as disconnecting means must have an interrupting rating sufficient for the available fault current. The NEC requires that the disconnecting means be readily accessible and located in sight of the capacitor bank or be capable of being locked in the open position. This ensures that personnel can quickly and safely disconnect the capacitor bank from the power source when necessary. If the disconnecting means is not within sight of the capacitor bank, it must be capable of being locked in the open position. This prevents accidental re-energization of the capacitor bank while maintenance or repairs are being performed. Locate the disconnecting means as close as possible to the capacitor bank to minimize the length of the conductors between the disconnecting means and the capacitor bank. This helps reduce voltage drop and improves the overall performance and safety of the installation. The disconnecting means must clearly indicate whether it is in the open or closed position. This is typically achieved through clear labeling and visible indicators on the device. Proper labeling helps prevent confusion and ensures that personnel can quickly determine the status of the disconnecting means. The NEC requires that the disconnecting means be suitable for the environment in which it is installed. For example, if the capacitor bank is located in a damp or corrosive environment, the disconnecting means must be rated for such conditions to prevent premature failure. If the circuit breaker in the main switchgear serves as the disconnecting means, it must comply with all the NEC requirements for disconnecting means, including interrupting rating, accessibility, and labeling. Ensure that the circuit breaker is properly rated and maintained to provide reliable protection and disconnection. The circuit breaker should be tested periodically to verify its proper operation and ensure that it can effectively interrupt fault currents. Use a separate disconnecting means specifically for the capacitor bank, rather than relying solely on the circuit breaker in the main switchgear. This provides an additional layer of safety and allows for independent disconnection of the capacitor bank without affecting other loads connected to the switchgear. Consider a capacitor bank installed in an industrial facility. The NEC requires that the disconnecting means be readily accessible and capable of being locked in the open position. The facility chooses to use a dedicated switch as the disconnecting means located within sight of the capacitor bank. The switch is clearly labeled to indicate its function and position, and it is ready for the maximum fault current available at that location. The switch is installed in a weatherproof enclosure to protect it from the harsh industrial environment. During maintenance, the switch can be locked in the open position to prevent accidental re-energization of the capacitor bank, ensuring the safety of the maintenance personnel. In another scenario, a large commercial building uses a capacitor bank to improve power factor. The circuit breaker in the main switchgear is used as the disconnecting means for the capacitor bank. The circuit breaker is readily accessible and has an interrupting rating sufficient for the available fault current. The circuit breaker is regularly inspected and tested to ensure its proper operation. However, to enhance safety, the building owner decides to install a separate, lockable switch near the capacitor bank. This provides an additional means of disconnecting the capacitor bank and allows for independent control during maintenance and emergencies. The choice of conduit for a capacitor bank installation involves several factors, primarily the environmental conditions, mechanical protection requirements, and local electrical codes. Electrical metallic tubing, or IMT, and rigid steel conduit, or RSC, are common choices, each with distinct advantages and disadvantages. EMT is a lightweight, non-threaded metal conduit that is relatively easy to install. It is suitable for use in dry, indoor locations where it is not subject to severe mechanical damage. EMT is typically made of galvanized steel or aluminum and is joined using fittings that are secured with set screws or compression. RSC is a heavy-walled, threaded metal conduit that provides excellent mechanical protection. It is suitable for use in both indoor and outdoor locations, especially where exposed to physical damage or corrosive environments. RSC is typically made of galvanized steel, although aluminum and stainless steel versions are also available for specialized applications. The NEC specifies where each type of conduit can be used. Generally, RSC is required in locations where greater mechanical protection is needed, such as in areas subject to physical damage from vehicles or equipment, or in corrosive environments where EMT may not provide adequate protection. EMT is permitted in many indoor locations where these conditions are not present. RSC offers superior mechanical protection compared to EMT. It can withstand significant impacts and is less likely to be damaged by physical stress. This makes it a better choice for installations where the conduit may be exposed to heavy machinery, vehicular traffic, or other potential sources of damage. RSC provides better protection against corrosion compared to standard EMT. The heavy galvanization and thicker walls of RSC make it more resistant to rust and corrosion, especially in damp or chemically active environments. However, special coatings or materials, such as PVC-coated RSC or stainless steel RSC, may be necessary in highly corrosive settings. EMT is generally less expensive than RSC, both in terms of material costs and installation labor. EMT is lighter and easier to cut than bend, which can reduce installation time and labor costs. However, the overall cost effectiveness depends on the specific requirements of the installation and the potential for future damage or corrosion. EMT is lighter and easier to handle than RSC, making it simpler to install, particularly in tight spaces or overhead applications. EMT can be cut and bent using relatively simple tools, while RSC requires more specialized equipment for cutting and threading. RSC requires threaded connections, which can be more time-consuming to install compared to the set screw or compression fittings used with EMT. Threaded connections also require proper sealing to prevent moisture ingress and corrosion. EMT fittings are generally quicker and easier to install, reducing overall installation time. Consider an industrial plant where the capacitor bank is installed in an area with heavy machinery and frequent forklift traffic. In this scenario, RSC would be the preferred choice due to its superior mechanical protection. The heavy walls of RSC can withstand impacts from machinery and prevent damage to the conductors inside. In a commercial building where the capacitor bank is installed in a dry, indoor electrical room, EMT may be a suitable choice. The environment is relatively benign and the risk of physical damage is low. EMT can provide adequate protection for the conductors at a lower cost than RSC. In coastal areas or industrial facilities with corrosive atmospheres, special considerations are necessary. Standard galvanized steel conduit may not provide sufficient protection against corrosion. In such cases, PVC-coated RSC or stainless steel RSC may be required to ensure long-term reliability and safety. When transitioning between different types of conduit, use appropriate fittings to ensure a secure and watertight connection. Follow all NEC guidelines and local electrical codes for conduit installation, including proper support, grounding, and bonding. Splicing conductors in an enclosure above the capacitor bank units and then feeding each unit with a single conductor is a viable method, but it is essential to adhere to best practices. The enclosure used for splicing must be appropriately sized and rated for the intended application. It should be large enough to accommodate the conductors, connectors, and any necessary splices without overcrowding. The enclosure must be rated for the environmental conditions in which it is installed, such as being weatherproof for outdoor applications or corrosion resistant in harsh environments. Select conductors of the appropriate size and type for the application, ensuring they are rated for the voltage, current, and temperature requirements of the capacitor bank unit. Use connectors that are specifically designed for the type and size of conductors being used. Ensure that the connectors are properly installed and tightened to provide a secure and reliable electrical connection. All splices must be made in accordance with the NEC and industry best practices. Use methods such as crimping, soldering, or using mechanical connectors to create reliable and durable splices. Insulate all splices with appropriate materials such as heat-shrink tubing or electrical tape to prevent short circuits and ensure electrical safety. Properly ground the enclosure to provide a low impedance path for fault currents and to minimize the risk of electric shock. Use grounding conductors of the appropriate size and connect them to the enclosure using approved grounding connectors. Label all conductors and components within the enclosure to facilitate identification and maintenance. Use clear and durable labels that indicate the function and destination of each conductor. Maintain accurate documentation of the installation, including wiring diagrams, conductor sizes, and connector types. This documentation will be invaluable for future maintenance and troubleshooting. Ensure that the installation complies with all applicable electrical codes and standards, including the NEC and local regulations. Obtain necessary permits and inspections to ensure that the installation is safe and code compliant. Regularly inspect the enclosure and conductors for signs of damage, corrosion, or loose connections. Perform periodic maintenance such as tightening connections and replacing damaged components to ensure the long-term reliability and safety of the installation. If any repairs or modifications are needed, disconnect the power supply to the capacitor bank units before commencing work. Use qualified personnel to perform the repairs and ensure that all work is done in accordance with applicable codes and standards. Consider a scenario where a capacitor bank is installed in a large commercial building. To simplify the wiring and distribution of power to the individual capacitor bank units, an enclosure is installed above the units to serve as a splicing point. The enclosure is sized appropriately to accommodate all the necessary conductors and connectors. All splices are made using crimped connectors and insulated with heat-shrink tubing. The enclosure is properly grounded to ensure electrical safety. The conductors are labeled to indicate their function and destination. The installation is inspected and approved by the local electrical inspector. In another scenario, a capacitor bank is installed in an industrial plant with a harsh environment. The enclosure used for splicing is NEMA 4X rated to provide protection against corrosion and water ingress. The conductors are selected for their resistance to chemicals and high temperatures. The splices are made using mechanical connectors that are designed for use in harsh environments. The enclosure is regularly inspected for signs of corrosion or damage, and any necessary repairs are made promptly. The 560 amp setting for the long-time pickup on the DS206E breaker in the main switchgear, whether it provides adequate protection for the capacitor banks, the ampacity of the conductors, the inrush current, coordination with other protective devices, and compliance with the NEC should be determined. The long-time pickup setting determines the amount of current the breaker will allow to flow continuously before tripping. It should be set above the normal operating current of the capacitor bank to avoid nuisance tripping, but low enough to protect the equipment from overloads. To determine if the 560 amp setting is appropriate, calculate the full load current of the capacitor bank and compare it to the breaker setting. The full load current can be calculated using the formula I equals kiloVars divided by the square root of 3 times voltage. The calculated full load current of the capacitor bank is 385 amps. The NEC requires that capacitor circuit conductors have an ampacity of not less than 135% of the rated current of the capacitor. This is to account for potential harmonic currents and overloads. The minimum required ampacity is equal to 1.35 times 385 amps, which equals approximately 520 amps. The breaker setting should be coordinated with the ampacity of the conductors to ensure that the conductors are protected from overcurrent. Capacitor banks can draw a high inrush current when they are initially energized. The breaker should be able to withstand this inrush current without tripping. Check the manufacturer's specifications for the capacitor bank to determine the expected inrush current and duration. The breaker should be coordinated with other protective devices in the electrical system to ensure that faults are cleared quickly and selectively. Perform a coordination study to determine the appropriate time current characteristics for the breaker and other protective devices. Ensure that the breaker and the capacitor bank installation comply with all applicable requirements of the NEC, including those related to overcurrent protection, conductor sizing, and disconnecting means. The NEC provides specific guidelines for capacitor bank installations in Article 460. Consult with a qualified electrical engineer to perform a thorough analysis of the capacitor bank installation and to determine the appropriate breaker setting. The engineer can take into account all relevant factors such as the full load current, conductor ampacity, inrush current, and coordination with other protective devices.